Today. I got yours, but I didn't get it done yet, sorry.
Okay.
But I've got it. Not a problem. Not to worry. I'll get it back to you on Wednesday. Yeah. Oh yeah, this is good. This is good. So let me comment first on the homework that just got returned. There's two things that more than, let's say, a couple of you had some issues with. The big problem that seemed to challenge people was this one about, show that if you have this condition, the condition that if for each element in the group and each element in the subgroup, if you compute G inverse HG for any element in the group G and for any element in the subgroup H, that this winds up back in H. So that's the hypothesis. Then let's see, then you had to prove, let's see, how was the question officially stated? Prove that every left coset's a right coset, or prove that AH equals HA, I forget. Prove that every left coset's a right coset, right? Every left coset is a right coset. Okay, the only two comments on the homework coming back are comments to be made in the context of this one problem. The first comment is this. The hypothesis that you're given, well, the two of you wound up proving every left coset's a right coset without using the hypothesis. Folks, there should be just these huge air raid sirens going off. If you're going to prove something without using the given hypothesis, then something is, I mean, I'll guarantee is 100% wrong, because in all of the problems that we'll do this semester, I got to be careful, in 99.9% of the problems that we'll do this semester, the hypotheses are required. In other words, if you remove the hypotheses that are given, then the conclusion doesn't necessarily follow. So please get in the habit of looking through your work before you submit it and make sure that you've actually used the hypotheses somewhere. The point is, if you're ever confronted with an expression that looks like this, where G is any element of the group and H is any element of the subgroup, what you get to conclude is that the result lands in the subgroup. What some of you tried to do was write down a stronger version of the hypotheses. What some of you tried to do was say, well, I have something, let's call it H1, that's in H. So, all right, at some point in your proof, you wound up with some element in H, and then you said, so there is a G in the group with, and let's call it H2 in H, with G inverse H2G equals H1. And I saw this on 3 or 4 of your papers, and folks, this hypothesis doesn't, at least not on the surface, imply this one. All this hypothesis says is, if you're confronted with an expression like this, that the result lands in H. It doesn't necessarily say that every element in H is of this form. It simply says that if you have something of this form, it's within the subset of H. And what this statement says is, if you start with something in H, then it gets hit by something of that form, and this is a stronger statement. Now, it might be the case that you could prove that that implies this, but you certainly can't just start here and say this is the hypothesis, because this statement is not logically equivalent to this one. Okay? So is not necessarily the same as this set of hypotheses, even though, admittedly, you'd prefer this hypothesis, because this gets you to the conclusion more directly. But all you get to start with is this. Okay? So be careful there. You can't sort of overstate what the hypotheses are telling you. You have to use the hypotheses as given. And most of you saw that the trick here is to sort of maneuver yourself into a position where it doesn't really matter what G is. Maybe G is the inverse of some element. So that if you have something that looks like A, H, A inverse, you can write that as A inverse inverse H A inverse, and so if you let G be A inverse, then you're looking at G inverse HG, and you wind up with something that lives back in H. Those of you that use the hint seem to have a little bit easier time with this. The hint was to somehow trade things in terms of the letter A rather than the letter G, so that you don't get tunnel vision thinking you have to have the thing called G sitting here. You could have something called A sitting there. You could have something called B sitting there. It doesn't really matter. Okay. The second comment is, and two of you commented on this, and this was really good. It's interesting, you actually wind up proving something that on the surface looks a little bit stronger than what you're required to prove. All you're required to prove is that every left coset is some right coset. In other words, all you're asked to prove is that each coset of the form AH is also of the form, well, that's what a left coset looks like, is also of the form a right coset for some. In other words, all you have to do is prove that AH is HB. So there's nothing explicit in the statement that you're trying to prove that says that you're required to prove that this left coset is the same as the right coset generated by the same element you started with. This really is all you're asked to prove. But all of you wind up proving, in fact, not only if you have this condition, is AH equal to a right coset, in fact, you prove that AH is equal to the right coset HA. So question, is this condition, every left coset is a right coset, the same as or somehow weaker than the condition that HA is AH, as all of you proved? And the answer is that they turn out to be the same. So here's an observation. I'm going to call it a proposition because we're going to need it in relatively strong form in about 10 minutes. The proposition is this: if every left coset of H is a right coset of H, then necessarily AH equals HA for all A. So if you give me the information that if you start with a left coset and it happens to be some right coset, I'll tell you which right coset it is. It's that right coset where you look at the right coset that's generated by the same element that generates as the left coset. And the reason is, if the hypothesis is that AH is HB for some B in the group, that's what we're told, that the left coset AH is some right coset. The question is, why can I conclude that the right coset that I use here is actually the right coset HA? And the answer turns out to be this. But wait a minute. It's always the case that the specific element A is in AH always. If you take a specific element in the group and you look at the coset that it generates, I don't care what subgroup you start with, any subgroup always contains the identity element. So you're always at least looking at AE. In other words, you're always generating the specific element A within its coset. So this is completely independent of this set of hypotheses. This is always true for any subgroup and any element of the group. So in this particular situation, if I've got an element in here, the hypothesis is that it equals this. So here, A is actually in HB, because these two sets are equal. And if it's in this set, then necessarily it's in that set. But now we're going to make a statement about right cosets. As soon as you have an element in the right coset, so HA equals HB, previous work that we did on cosets, the work being, if you have an element that lives inside a coset, then the two cosets have to be equal. Because what? We know that any two cosets, either left cosets or right cosets, as long as you're comparing apples to apples, any two left or right cosets are either identical or they're disjoint. Well, these aren't disjoint because A lives inside here. So necessarily the two cosets have to be identical. So the hypothesis that AH is HB actually leads to the conclusion that HB is HA. And so the conclusion is that, in fact, not only is AH equal to HB, AH is actually equal to HA as well. You might say, wait a minute, how can we have two things equal to each other? The answer is, remember, folks, you can very easily find different elements in the group that generate the same left or right coset. And that's why I had you in the homework do a whole lot of examples of compute the right cosets, then compute the left cosets, and tell me which are equal and tell me which aren't equal. And the observation is sometimes you have different elements that produce the same right coset or different elements that produce the same left coset. In fact, that's what's going to make the construction that we're going to start doing today so, well, unfortunately so mysterious or so uncomfortable at the beginning until you get a feel for it. All right, so that's a comment. You weren't necessarily asked to prove that HA is AH. All you were asked to prove is that AH is some HB, but all of you proved that AH is in fact HA. All right, that's good. And that in fact is true. Okay. Questions there? Comments? All right. So there's sort of both the wrap up to the homework and an important piece of information that we will wind up using today. So let me, and this was good. What we did last Wednesday for the last 10 minutes was I sort of just started spewing about what it is that we're going to do for essentially the next week and a half in here. I gave you the overview without writing anything down. What I'm going to do today is start writing things down. What we'll do on Wednesday is you'll have a quiz on some of the stuff that we'll do today just so that the ideas start getting pounded in your head and you're actually writing them down yourself. And then on Wednesday we'll do the same thing. We'll sort of step back and look at the big picture again. And in the context of it all, we're just going to keep doing computation after computation after computation so that hopefully you start seeing the patterns and start understanding what these structures are that we're going to work with. Okay? So here's the new big idea. New big idea. These are usually called factor groups. Another phrase for them is groups of cosets. And this is section 13. We're skipping section 12. I'm not sure I mentioned that on last Wednesday. We're going to skip section 12. We may come back to it at the end of the semester if we have time. Those are 14, sorry. And we're skipping 13?
No, we skipped 12.
Oh, yeah, okay. So I'll say sections 13 through 15. Because homomorphisms is sort of the lead-in to what we're doing with these groups of cosets. All right, here's the goal. We have a set. The given information is this. You start with a group, G is a group, and H is some subgroup of G. And throughout the discussion, folks, once you write down the group and the subgroup, those are meant to stay as they are throughout the discussion. You're not going to change what subgroup you're going to look at or change what group you're going to look at. You're going to build a new group, maybe, based on these two pieces of information. The original group that you start with and some subgroup that you've chosen. Now look, you got a lot of choices to begin with. You got a lot of choices of groups to start with, and you got a lot of choices within that group of what subgroup you want to look at. But once you've made those two choices, everything's now fixed. And all the discussion is given in terms of that context. Okay, well, what is a group? A group is nothing more than a set, together with a binary operation on that set, that has three additional properties: associativity, the existence of an identity, and the existence of inverses. What we're about to do is, based on this data, produce new groups. Now, the thing that's the hardest for students to wrap their heads around is that the elements of these new groups that we're about to describe, the elements are sets. So a thing in this new group is a set. In fact, more specifically, a thing in this group, an element of this group, is a coset of H in G. Well, cosets are just sets. They're not groups. They're just sets. Okay, one of them happens to be a group, this coset consisting of H itself. But in general, they're just sets. And what we're about to do is come up with a process by which, if you take the group, you take the subgroup, You then form all the cosets of the subgroup sitting in the group. You did that a lot in the homework that just came back. You get a set of sets. And that's, I think, where students have a little bit of trouble. It's a set of sets. So inside the set, you're looking at a bunch of sets. And the goal is to define or provide some sort of binary operation on those sets. In other words, some sort of operation where if you hand me two of these sets, you can combine them together and produce one of the sets. Okay. And moreover, once we write down that binary operation, once we write down this method of taking any two of these sets, in other words, taking any of these two, I'll focus on left cosets for now, any of these two left cosets, and combining them together to get another left coset, once we write that down, that's where the hard work's going to be. It'll turn out that that definition of a binary operation on the collection of cosets actually gives a group structure on the collection of cosets. So just a little preview of what's about to happen. We're about to write down all the left cosets of a given subgroup. That collection of sets, where we view each of the cosets individually as an element of this big set of cosets, that collection is eventually going to become a group. In order to make it into a group, we need to, step 0, define a binary operation on that collection of cosets. That'll be hard. That's going to take us a long time to do. But once we've done that hard work of actually defining the binary operation on this collection of sets, that binary operation will almost clearly or easily be shown to be associative, have an identity, and show that the existence of inverses happens. So it's a little bit counterintuitive because typically in the past you'll be handed a set, you'll define this thing, it's sort of trivial to show that it's a binary operation on the set, and typically the hard work is showing, well, usually not associativity, but maybe the existence of an identity or the existence of inverses. Here the hard work is going to be in showing that we actually have a binary operation on this collection of subsets. And then once we do, then things will be pretty easy. Okay, so here's the goal. We seek, good word, to define a binary operation on the set. For now, folks, I'm going to call it script S. We're going to give it another, I don't know, more standard name once the process is all said and done, of left cosets of H. Okay? So I've given the set of left cosets a name. I've called it script S. It's the first time we've given that set a name. I know how big the set is. Remark, how many elements are in this set? Or another way of asking that question is, how many left cosets are there of H in G? The index of H in G. Now, if it happens to be the case that this group is a finite group, in that case, we happen to know what that number is. It's this number, but only if you start with a finite group. And the point is, the construction that we're about to look at holds regardless of whether or not the group happens to be finite. The group could be infinite. And in fact, the number of cosets of H in G could be infinite. So I'm not restricting our attention only to finite groups or only to situations where there's only a finite number of left cosets of H in G. It's just if I happen to look at that very important situation, I can actually count how many elements are going to be in this group. All right. We'll look at some specific examples in a minute. So here's what we're going to do. So the goal is, rephrased, here's what we want to do. We want to define, I don't know what to call it. How about, I don't know, start with a little circle around it or something like that? I mean, it's a special binary operation. It's not composition. And it's not the star of the group necessarily. Something else. So let's just call it something new. on this set of left cosets in order to make it into a binary operation. In other words, we want to take any two left cosets and somehow define what this means and spit out some left coset. So that's the task, somehow to come up with a systematic or reasonable way by which you take any two left cosets of H, these individually are sets, okay, that's fine, and somehow combine them, whatever that means, to kick out another left coset of H. Well, and this is what I was sort of starting to get at last Wednesday, it turns out that there are at least two not unreasonable places to look to try to do that. Let me give you one possibility. One possibility is, all right, folks, all the things in this set are just, well, they're elements of the coset. But in the end, they're simply elements of this group. And this is some collection of elements in that group. So individually, I've got this collection of elements in the group, and I've got another collection of elements in the group. So the following process at least would make sense. Just sort of, what do they call it, FOIL everything? Multiply everything in here with everything over here and see what you get. If you got two elements in this left coset and two elements in this left coset, combine that one with that one, and that one with that one, and that one with that one, and that one with that one. It's at least a reasonable way of somehow smashing together the elements in this set. And see what you get. All right, that at least would be a reasonable way of taking these two subsets of G and smashing them together to get another subset of G. It's just, what's the possible problem with that? You might get more elements. Exactly right, Jared. You might get elements that don't form a coset. I mean, for example, we could look ahead a little bit and say, maybe it's the case of I've got two elements in here and two elements in here. I combine that with that, and that with that, and that with that, and that with that. I mean, presumably, maybe four elements get kicked out. And hey, if your cosets each have two elements, every coset then only has two elements. And if you kick out four elements, you haven't defined a legit binary operation on the set of left cosets. You kicked out something that's not in the set. That would be bad. In fact, I'm about to show you an example of where that happens, unfortunately. Okay. So here's possibility one for defining a binary operation on script S. Possibility one, possible binary operation number one on script S. Define AH star with a circle BH to equal, I'm going to call it the set product of AH with BH. And set product simply means exactly that process I just described in words. Take everything in this set and simply combine it with every possible thing in this set and see what you get. For example, let's do this. Let G be S3 and let H be the subgroup of G generated by mu1. Well, that turns out to just be a two-element subset, I and mu1. Let's write out the left cosets. Left cosets. Let's see, did you do this one for your homework? I forget if this one actually came up, but whether it did or didn't, it's a good exercise. Here they are. Let's see. Row 1H. So that's row 1I. So that's row 1 mu1. So that's row 1 and mu3, it turns out. I'll let you haul out your table for S3 if you want here. Okay. So row 1H turns out to be row 1 times I, which is row 1, and row 1 times mu1, which is mu3. So just for what it's worth, we also by default have just realized that this is the same as the left coset mu3, because as soon as you find an element in a left coset, that is the coset generated by that element. Here's the second left coset, row 2h. Just do the appropriate product. So that's row 2 times I, so we know row 2 is in there. We always get that one for free. And then row 2 mu1 turns out to be what? Somebody have the table in front of them? mu2, thank you. So that by default, this also happens to be mu2h. And if we do row 3h, let's see what we get here. Oh yeah, there's no row 3. Huh. Oh yeah, there's row 0, pardon me. So if we do row 0h, that's easy. That's IH. So row 0 is I here in this notation. So that's row 0 and mu1. So that happens to be mu1h. So there are the 6 left cosets of H inside G. Now, let's see whether or not this proposed binary operation on the left cosets of H and G actually kicks out another coset. So let's compute, how about something like, how about, well, this, yeah. So the request is to take any two of these left cosets. How about this one, row 0, mu1. There's a left coset. That's my AH. Of course, I could call it row 0H or mu1H. It doesn't really matter here. There's a left coset. Let's combine it with another left coset. How about row 1, mu3? And let's see what we get. Well, this is, by definition, the set product. In other words, what I'm going to ask you to do is simply pound out all of the possible combinations that you can, where you take something from this set and combine it with something from this set. So the first thing is row 0, row 1. The second thing is row 0, mu3. The next thing is mu1, row 1. The next thing is mu1, mu3. And let's see what we get. Well, we get row 1, because that's row 0, row 1. And we get row 0, mu3. What's that? Mu3, that's easy. And we get mu1, row 1. Does somebody have that? mu1, row 1. mu2. And then we do mu1, mu3. Somebody have that? Row 2. Get a perfectly good subset of the group, but we don't get a subset of the correct form. We don't get a subset that happens to be a coset of H and G. Looks, there's only 3 cosets of H and G. Here they are. If nothing else, each of the cosets of H and G have 2 elements, and I've just written down a subset of the group that has 4 elements. So the issue is problem. The result is not another left coset. Left coset of H in G. I'll rephrase that in terms of binary operations on set, i.e. when we did row 0 mu1 and we start it with, circle started or whatever that we're calling this thing, row 1 mu3, that process did not give us something back in the set we're interested in. It didn't give us something back in script S. So, star, defined in this way, is not a binary operation on script S, at least in the situation where you happen to start with this particular group and this particular subgroup. Now, I'm not claiming that, well, it might be the case, folks, that if you started with a different group and a different subgroup and you started pounding these products out, maybe you will get another left coset of the subgroup. Maybe you will. But at least in this particular example, the point is, if we start with this particular group and this particular subgroup, if we try to define a binary operation on the collection of left cosets simply by hammering them together, not an unreasonable thing to do, the issue is that what gets kicked out is perhaps not another left coset. So in general, this process will not give us a good binary operation on the collection of left cosets. Okay. All right, so too bad. So possibility one, reasonable possibility one for trying to define some sort of binary operation on the collection of left cosets, crapped out because it didn't kick back a left coset. All right, so let's reinvent the wheel here and say, okay, if at first you don't succeed, let's try another approach. Here's a good other approach. What was the problem with trying to do set products? The problem was what got kicked out wasn't another left coset. Now if somebody just handed you these two left cosets and said, all right, here's what I want you to do. Tell me a reasonable left coset that you might want to associate with that left coset and that left coset under some binary operation. Anybody got a reasonable guess? Give me a left coset that might be a reasonable output when you try to combine these two. Anyone? What should I put here? How about A star B? Okay. Good idea. So here's a good definition. So let's try possibility number two. So here's possibility number two. Because possibility one crapped out, possibility two is simply deem, forget the set multiplication crap, deem AH, what should we call this one now? Star, or something like that, BH. I'm coming up with some presumed new binary operation equal to ABH. Then here's what we've done. We've simply eliminated the problem that came up in possibility one. We simply said, all right, take this left coset and combine it with this left coset and simply deem the output to be this left coset. Good plan. At least what gets kicked out is another left coset. Okay, so now, can anybody predict what the issue is going to be with this possible definition?
There's a lot of different ways to write a particular concept, so it could be now more defined.
Beautiful. That's exactly what's going on. So what Jared just suggested is this. Look, if I hand you a left coset, there's lots of different ways of writing it down. For instance, this particular left coset could be viewed both as row 1H, but equally as good could be viewed as mu3H. This particular left coset could be viewed as that, or it could be viewed as that. And so what's about to happen is we have to make sure that regardless of how we name our left cosets, that the combination of the two producing what you get when you take the two coset representatives and combine them is well defined. It's exactly the same issue, folks, that we looked at in day one in here. And the context there was rational numbers, where it was possible to have two different ways of describing the same rational number. 1/2 and 3/6. Here there's, for example, two different ways of describing this left coset. Row 1H or mu3H, two different names. So if I'm going to try to define a binary operation corresponding to those things, I have to be careful that the operation is well defined. And guess what? It's not going to be well defined. But let's do an example. Consider these. Consider if I look at, let's do this. If I do row 1 mu3, and I ask you to double star it with this one. This one, row 2 mu2. So I'm asking you to double star this one with that one. What left coset gets kicked out? Well, here's the issue, folks. This thing how do you figure out what gets kicked out? The first step is you have to take the coset and write it in one of these forms. All right, how about let's first write it as rho 1h. And then I'm asking you to double star that with, let's see, rho 2h. Is that what I want to do here? Yeah. So what should you get? Well, if this is the definition of what double star is, I've now taken these two cosets, I've given them names of the appropriate form, and now the way you're supposed to combine cosets given in this form is you're simply supposed to take the two coset representatives. That's the definition of what this proposed binary operation is supposed to do. Which gives what? Well, rho 1, rho 2h is rho 0h, which is h. In other words, which is this left coset. The left coset, rho 0, mu 1. So if I combine these two left cosets by calling the first one rho 1h and calling or naming the second one rho 2h, then the result of that particular combination is just the coset h itself. Now, we're about to see the issue. And again, I want you to keep in mind the issue that happened when you tried to, like on exam 1, take two rational numbers and try to combine them together, and then take two other rational numbers that represent the same rational numbers and try to combine them together and see what happens. But also, I can take the same two left cosets, rho 1, mu 3, double star with rho 2, mu 2. In this particular situation, what I'm going to choose to do is write this as mu 3h. And I'm going to choose to call this one mu 2h. And in this situation, let's see, what is mu 3, mu 2? Well, by definition, this is supposed to be mu 3, mu 2h. And what is mu 3, mu 2? Is rho 2. Which is, oh, let's see, rho 2h is this one right here. Is rho 2, mu 2. So here's what we just did, folks. We took exactly the same two left cosets, rho 1 mu 3 and rho 2 mu 2. Here they are again, rho 1 mu 3 and rho 2 mu 2. If we chose these particular names for those two particular cosets and ran them through this proposed binary operation, here's the coset that got kicked out. On the other hand, again, we take the same two left cosets, but we choose to name them this time instead by these other names and then run them through the process. The issue is that what gets kicked out is a left coset. That's not the problem. It's just what gets kicked out is the different left coset than got kicked out the first time. So the issue is because this and this are not equal, punchline is, so this second proposed binary operation is not well defined. Too bad. So we're crapping out here. So we've tried on the surface what looked to be the two reasonable possibilities for coming up with a method or an algorithm or a definition of how to take two left cosets of a subgroup sitting inside a group and combine them to produce another left coset. So we haven't even gotten this process off the ground yet. We haven't even written down a binary operation. Okay. Well, it sort of in-rides the hero here. The punchline is, folks, that if you just hand me a group and you hand me a subgroup, it's obviously not always the case that if you try to define either one or the other of these two proposed binary operations on the collection of left cosets that you get another left coset, or that you at least get a well-defined binary operation on the set. But what we're about to see is if you start with a special sort of subgroup, then it is the case that possibility 1 gives you a binary operation on script S. In other words, it is the case that possibility 1, the possibility where you just hammer together all of the elements that you're looking at in the appropriate order, actually kicks out another left coset. So that gives you a binary operation on script S. And the miracle, or what's incredibly nice and beautiful about this particular idea is, in exactly the situations where when you take any two left cosets and hammer them together by this set product and you get another left coset, those will be exactly the same types of subgroups that have the property that if you define this type of binary operation by simply deeming AH double star BH to be ABH, that's going to be well defined. And that's what's going to give us a binary operation on the collection of left cosets. So the question is, what's sort of the magic property that will allow not only the method of combining left cosets to get another left coset described in possibility 1, not only for that to give another left coset, but for the other one to be well defined. What's the magic property of the subgroup that makes that happen? Answer, that every left coset is a right coset. That's why we've been playing up this particular property so much over the last week and a half. So here's the miracle. Miracle. Turns out that if you happen to start with the same sort of data, a subgroup H sitting in G, and furthermore, H happens to have the property that every left coset of H is a right coset of H, then it turns out everything works. So there's the statement of what's about to happen from an emotional point of view. Now let me write down some of the technical details from a more mathematical point of view. What we're going to show is if we happen to start with not just your favorite subgroup sitting inside your favorite group, but your favorite group and your favorite subgroup sitting inside that group that happens to have this extra property, that every left coset of H in G is also a right coset of H in G, then if you go back and try to define a binary operation on the collection of left cosets by simply doing set product, you'll always get another left coset. In other words, that'll give you a legit binary operation on the collection of left cosets. But since we're not going to pound through all the details of this, I'll just sort of mumble it under my breath. And if you were to take the same sorts of subgroups and go back to possibility 2, the situation where you deem the binary operation by combining two left cosets to simply be the product of the coset representatives, in fact, that process will give you a well-defined binary operation on script S as well. But since we're not going to focus on this as much, I won't play that up as being so important. The punchline will be this, because this is how we'll actually do the operations here more formally. Here's the definition. I'm going to give this a name, definition. If H is a subgroup of G, then H is called a normal subgroup. And typically we'll just say H is normal in G in case this property holds. In case every left coset of H in G is also a right coset of H in G. That's what the word normal means, that every left coset of H is a right coset. All right. A bit of notation and then a quick comment, and then we'll look at some examples. Notation, if this happens, we don't have to write this, but typically we do. We write, just for shorthand, H. Well, let's see, we know what the notation for subgroup is. It's this less than or equal to sign. It's this sort of sharp inclusion sign. If the subgroup happens to be normal, then we close up this third line here and make a little triangle. So if we write this, it means a lot. It means not only is H a subgroup of G, but it has the property that every left coset is a right coset. Now, by a previous remark, the remark that I made right at the beginning of today in the context of the homework question that came back, every left coset is a right coset, is the same thing as saying that for every A, AH not only is some HB, but in fact AH is HA. So this is the same as saying AH is HA for every A in G. So a subgroup of a group is normal in case, not just the statement every left coset is a right coset. In fact, the statement that every left coset AH is in fact its sort of mirror right coset HA. Right. So I'm going to write down the key proposition because I want to show that this particular condition leads to where we want to be. Will, question?
Would that make our group abelian?
Oh, great question. So the question is, does this necessarily, let me back up. Make which group abelian?
G.
No. So the question is, does this condition necessarily give that G is an abelian group? And the answer is no, because we did remember a homework problem. Which number was that? Numbers 9 and 10 in the one that came back tonight? Section 10? Section 11 was it? Something like that. Section 10? Example. Let's see. What was G there? D4? And what was H? Yeah, the subgroup generated by row 2. So this is row 0, row 2. Then you showed in, what was it, section 10? Section 10, problems number 9 and 10. H is normal in G. And how'd you prove that? You just pounded them out. You pounded out all the left cosets and you pounded out all the right cosets. But I'll put as a remark, the original group G is not abelian here. So Will's question, does it necessarily require G to be abelian in order for this to happen, is no, but I hesitate to put this in here because then it might give you the wrong impression, but hopefully having written down this example first, you won't get the wrong impression. If it happens to be the case that the original group that you start with, this group G, is abelian, if it is, then it turns out, regardless of what subgroup you write down, it'll be normal. If G happens to be abelian, then every subgroup will H will be normal. Will be normal in G, and the reason is, well, wait a minute, if you give me a left coset AH, if the whole group is abelian, if G is abelian, then every one of the products that you do here, AH, is going to be the same as HA, so you just flip it around. So if the entire group is abelian, then this condition comes for almost free. It's almost automatic. We'll get back to this observation in a minute. I was sort of hoping to keep it under the rug for another couple of minutes, but since it was asked, that's fine. But I don't want you to get the wrong impression. What's going on with the question of a subgroup being normal inside a group is a significantly bigger question than simply is the group abelian. And here's the good example to keep in mind. Okay. In fact, let me give you another example just to hammer it home. Example, if G is S3 and H is the subgroup generated by row 1. So this is row 0, row 1, row 2. Then H is normal in G. And the reason is, I'll put it in parentheses here, I'm going to let you do the pounding. Just pound them out. Pound out, row 0 H equals, which happens to equal H row 0. Compute. Row 1H equals H row 1. Compute. Etc. You got 6 things to do. 6 things. Just pound them all out. The last one will be what? Mu 3H or something like that. Equals H mu 3. Compute. I'm leaving out lots of admittedly tedious computations, but it's stuff that's at the same level of the stuff that you did in problems 6, 7, 9, and 10 in section 10 for the homework that just came back. And they all turn out to be the same. So here's another example of a normal subgroup sitting inside a group that's not abelian. This is another good example to write down for the following reason. Inside this group, we've just written down a normal subgroup. But in this same group, if we were to choose a different subgroup, it might not be normal. Okay? But contrast with in S3 equals S3. So the same group, if we choose instead the subgroup consisting of the subgroup generated by mu1, so that's row 0 mu1, then H is not normal in G. And the definition of normal is that every left coset is a right coset. That's the definition. So in order to show me that some subgroup is not normal, all you have to do is produce a single left coset that's not the same as the corresponding right coset. Try to choose wisely here. It'll turn out, folks, if you try to choose the left coset that happens to be the subgroup itself, the subgroup itself is always a left coset and it's always a right coset. So don't look there if you're trying to show that the subgroup's not normal. It turns out you can show that if you compute mu2, row 1 H, that's not equal to H row 1. And all you need is one particular situation where the left coset doesn't equal its corresponding right coset in order to conclude that the subgroup's not normal. In fact, if you wanted, you could have picked the example provided by problems 6 and 7 in section 10, because there you started with D4, right? And you looked at a specific subgroup. I think it was, what was it, row 0 delta 2 or something like that. I forget what subgroup you started with in question 6 there, but the point is, yeah, so row 0 and mu2, yeah. So in that particular case, if you start with the subgroup row 0 and mu2, that's a subgroup, and it turns out to be not normal. So I'll throw this as a non-example. Contrast with G is D4, H is row 0, mu2 is not normal. And maybe that's even a little more compelling because in this situation, the subgroup I gave you had 3 elements sitting inside the group. This one happened to be normal. the subgroup inside that same group, which wasn't normal, only had 2 elements, you might think, all right, well, give me an example where you've got 2 subgroups and they each have the same number of elements, where one's normal and one's not. And here's a good example of that. This is a normal subgroup of the group D4. It has 2 elements. This is a subgroup with 2 elements of D4. It's not normal. So let me get to the most important punchline involving normal subgroups, which is what we're about to show is if you start with a normal subgroup of a group and you start doing set products, that the set product of any left coset with any other left coset will kick out another left coset. In other words, that possibility 1 of a binary operation on the collection of left cosets actually works as long as you start with a normal subgroup. So here's the big theorem. Suppose H is a normal subgroup of G. Group of G. I'll put it in parentheses, i.e. the hypothesis, because I'd like you to start using this notation. H is a normal subgroup of G. We'll simply write that here. Then here's the punchline. Then the set product of any 2 left cosets of H and G produces another left coset. Of H and G. Let me rephrase that. Rephrased, this binary operation, the proposed binary operation number 1, proposed first binary operation on the set S, on the set script S of left cosets given by AH, I called it star with a little circle around it, BH, equal to the set product of AH with BH, gives a binary operation on S. Operation on script S. So if we happen to start with one of these nice subgroups, then the way we'd like to combine these things actually works. All right, here's the proof. In fact, here's what we're going to show. We show that in this case, that when we compute AH, multiply everything in there with BH, that we actually get that left coset. And I say, wait a minute, I thought you were worried about well-defined nonsense. Well, I was when I simply deemed AH combined with whatever we called the thing, double star BH, to be that. But now I'm giving you a method for computing what it means to take that with that. And folks, the definition of how you combine the 2 left cosets is independent of what I call the thing. Just take this left coset. I don't care if you call it AH, A prime H, A double prime H. Take this left coset. All you're doing is forming set product. So it's independent of the name. So the operation is well defined. The question is whether or not what it kicks out is another left coset. And the answer is yes, it does kick out another left coset. And I'll tell you which one it is. That one. Okay, here's how to do this. To do it, here's the hard part. The other part will be easy. Hard part meaning here's the part that actually requires the subgroup to be normal. We'll show that if you do set products, that you get something that's always inside that left coset. So here's what we have to do. In other words, we show Well, let's see, what does a generic element inside the set product of that left coset with that left coset look like? It looks like you take something in here that for every element, let's call it AH1, that's what a generic element in here looks like, and for every BH2 in this other guy, BH, that when we combine them together, AH1, BH2 is actually in ABH. How are we going to do that? You might say, well, just flip those two. Then you'll get AB and then H1, H2, but since H1 and H2 are each in H and the subgroup is closed, then you'll get something in here. But folks, I can't just flip things because I'm not necessarily in the Abelian group. Of course, if I was in the Abelian group, I'd be able just to flip them around and I'd be done, but I'm not in general. But the hypothesis that I have is that the subgroup is normal. So here's the point. But the hypothesis says that every left coset is a right coset. In particular, this left coset is, some right coset. But not only is it some right coset, I know what right coset it is. It's that right coset by hypothesis. That's the normal hypothesis. That's the hypothesis that H is normal in G. The hypothesis that H is normal in G. So what? In particular, anything in this set is in that set. In particular, I'm going to identify something in there. This element, H1b. Well, wait a minute. H1b is, by definition, in that right coset. That's not an issue. It's just something in H times b. But that's BH. That's the hypothesis. It's the hypothesis. So H1b, is in BH. In other words, that thing, H1b, can be written as B times, H3 for some H3 and H. So it means to be in a left coset. It means you can write it as whatever the left coset representative is combined with something in the subgroup. So here's what we're going to do. So, AH1BH2, this is what we're interested in saying something intelligent about, equals, well, I'll just slide some associativity in here. Associativity abounds. I can group things anywhere I want. Equals A, but wait, H1b is BH3. Just substitute. We're just substituting what we observed about H1b. Which equals AB. I'll combine that with H3, H2. But wait a minute. H3 is in H. And H2 is in H. And H2 is in H. So H3, H2 is in H. So the punchline is that this is in ABH. And so what we've just shown is that if the subgroup is normal and you do set product with two left cosets, then necessarily the result lives inside the left coset ABH. So what we've just shown is this. So we can conclude that one direction is true. AH, do the set product with BH, is contained in ABH. Notice, folks, to get there, we needed the hypothesis that the subgroup is normal. Now, in order to convince you that this set product is actually equal to ABH, because that's the goal, we just have to show inclusion the other way. But inclusion the other way is going to be easy, and it's not going to require that the subgroup is normal. Inclusion the other way always happens. For the other direction, to show that ABH is contained in the set product of AH with BH, that's easy to do. Pick something in here. Pick ABH1 in ABH. We have to show that it's in here. And I'll do that just in one step here. I have to somehow convince you that I can write ABH1 as something of the form, something in that left coset combined with something in this left coset. But ABH1 can be written as AEBH1. No problem there, that's just A. So I've just used associativity and the identity element of G, because that's just A, so that's ABH1. Oh, but wait a minute, this is in, well, that's in AH. Why? Because it's something in, it looks like A times something in H. How do I know the identity's in H? Because H is a subgroup. It contains the identity element. So this is in AH, and I've multiplied it by or combined it with something that's in BH. So check. And you'll notice to go the other way, I didn't need that the subgroup was normal just to get the containment going the interesting way, or the hard part. That's the easy part, that second part. So here's the big theorem. It says that if you start with a nice subgroup of the group, then if you form set product of two left cosets, you necessarily get another left coset back. Okay. Questions, comments? So we've now written down a couple of things that are equivalent. To say that every left coset is a right coset is equivalent to saying that every left coset AH equals its corresponding right coset HA. For the homework, in problem number 28, what you showed is that if you have this property that G inverse HG is an element of H for every element G in the group, then necessarily every left coset is a right coset. So in fact, you've written down in problem 28 a condition that implies the subgroup is normal. That condition actually happens to be an if and only if statement. If you have that condition from problem 28, the subgroup's normal. Conversely, if the subgroup is normal, you can show that that condition applies. So in fact, now there's three equivalent statements. The subgroup is normal. AH, the left coset, equals the right coset HA for every element in the group. Statement 3 that's equivalent is for every element in the group, call it A or call it G, I don't care. If you take G inverse and you combine it with something in the subgroup H and then you look at G, you get something back in the subgroup. That's condition 3, that's equivalent. We've shown now that each of those conditions implies that if you do the set product of any two left cosets of H, you get another left coset. That's condition 4. And what I'm going to leave out is that condition 4 is actually equivalent to those. That's sort of a strange statement, so I won't write it down or prove it. But the statement is, if it's the case that you have a subgroup with the property that whenever you do set product of any two left cosets, that you get another left coset back, it turns out you can show that that implies that the subgroup is normal. Now there's this other condition floating around, which is, how do you make possibility 2 work out? How do you make it, or hopefully rig it, so that you're looking at a subgroup sitting inside a group that has the property that if you simply deem AH double star BH to be the left coset ABH, that that's well defined, answer, you throw that on the stack too. That's equivalent to all these conditions. So there's a lot of things that on the surface look completely different, but in fact turn out to be completely equivalent in the end, and equivalent to this condition that the subgroup is normal. We just go through them once more, and then we hand out a sheet about those, and then we'll call it a night here. They are that the subgroup is normal, in other words, that every left coset is a right coset. They are that every left coset AH equals its corresponding coset HA. They are the problem 28 condition that G inverse HG is contained in H for every element G in the group and every element H in the subgroup. They are that when you take the set product of any two left cosets, you get another left coset back. And they are that the binary operation on the collection of left cosets defined by deeming AH double star BH to be ABH is well defined. All right. Yeah. So let me give you the homework and let me tell you what's in store. So we're going to have a quiz. So the first chunk of the homework is that quiz 3 happens this Wednesday. quiz 3, Wednesday, will be the first, I don't know, 5 or 7 minutes of class. And what you'll be asked to do on Wednesday is write down for me the conditions that I just provided you that are equivalent. And what I'm going to do is I'm going to hand you the statement of what I'm going to have you do on Wednesday, and I'm going to hand you all the solutions. So if nothing else, all I'm going to ask you to do on Wednesday is sort of spit back at me. Well, I've listed it out as 6 conditions. I've written the subgroup being normal. I've listed out condition 6, and we haven't talked about that yet, but I'll have you write it down for me on Wednesday anyway. It turns out, this is the big punchline, folks. We know now how to write down a condition on the subgroup, which will ensure that we can write down a well-defined binary operation on the collection of left cosets. The condition is you start with a normal subgroup, and in the end, the punchline is that not only do you get a well-defined binary operation on the collection of left cosets, that in fact that binary operation turns the collection of left cosets into a group. And that's the group that we're going to start studying on Wednesday. So statement 6 is, not only do you get a well-defined binary operation, but that makes the collection into a group. We haven't proved that yet, but you understand what that statement means. We'll prove that right after you're done taking this quiz on Wednesday. But as I mentioned before, the hard part is the part that we just proved. The hard part is to show that if you start with a normal subgroup, that you at least get a binary operation. You at least have sort of the primordial goo that you could potentially build a group from. Writing down the 3 properties, associative, existence of an identity, and existence of inverses, is only going to take us 10 minutes at the beginning of class on Wednesday, because we've done all the hard work in actually getting to the point where we've got a binary operation. Okay, so when you walk in on Wednesday, I'm going to hand you a sheet with just the first sentence there. Let H be a subgroup of G. The following statements are equivalent. Actually, I'll probably give you number 1, and then I'll let you crank out statements 2 through 5. Okay, here is the remainder of the homework. And this homework will be due on the standard homework schedule, so it'll be due a week from Wednesday. This homework assignment includes a homework sheet together with some problems from the text. So here's the collection of problems that I'll have you do. There we go. And if you're watching on video or online, then I'll post these. I should have these up on the website by tomorrow, and I'll post the homework there too. So here's home. Again, quiz Wednesday. The remainder of the homework assignment is due a week from Wednesday. So when the heck is that? The 17th? Wednesday, October 17th. I want you to first do in section 11 problems 16, 18, and 21 through 26. I want you to turn in 16 and 24. Those are questions about isomorphisms between direct products of abelian groups. Then I want you to do this sheet that I just handed out, sheet on normal subgroups. And I want you to turn in the entire sheet. So that's a turn-in piece of the assignment. And then in section 14, problems 9 through 16, 21, 24, and 40. And I want you to turn in 12, 21, and 40A. So this will be a relatively large assignment. Okay. All right. Today. I got yours, but I didn't get it done yet, sorry.
Okay.
But I've got it. Not a problem. Not to worry. I'll get it back to you on Wednesday. Yeah. Oh yeah, this is good. This is good. So let me comment first on the homework that just got returned. There's two things that more than, let's say, a couple of you had some issues with. The big problem that seemed to challenge people was this one about, show that if you have this condition the condition that if for each element in the group and each element in the subgroup, if you compute G inverse HG for any element in the group G and for any element in the subgroup H, that this winds up back in H. So that's the hypothesis. Then let's see, then you had to prove, let's see, how was the question officially stated? Prove that every left coset's a right coset, or prove that AH equals HA, I forget. Prove that every left coset's a right coset, right? Every left coset is a right coset. Okay, the only two comments on the homework coming back are comments to be made in the context of this one problem. The first comment is this. The hypothesis that you're given, well, the two of you wound up proving every left coset's a right coset without using the hypothesis. If you have something in this form, it's within the subset of H. And what this statement says is, if you start with something in H, then it gets hit by something of that form, and this is a stronger statement. Now, it might be the case that you could prove that that implies this, but you certainly can't just start here and say this is the hypothesis, because this statement is not logically equivalent to this one. Okay? So is not necessarily the same as this set of hypotheses, even though, admittedly, you'd prefer this hypothesis, because this gets you to the conclusion more directly. But all you get to start with is this. Okay? So be careful there. You can't sort of overstate what the hypotheses are telling you. You have to use the hypotheses as given. And most of you saw that the trick here is to sort of maneuver yourself into a position where it doesn't really matter what G is. Maybe G is the inverse of some element. So that if you have something that looks like A inverse, you can write that as A inverse inverse H, A inverse. And so if you let G be A inverse, then you're looking at G inverse HG, and you wind up with something that lives back in H. Those of you that use the hint seem to have a little bit easier time with this. The hint was to somehow trade things in terms of the letter A rather than the letter G, so that you don't get tunnel vision thinking you have to have the thing called G sitting here. You could have something called A sitting there. You could have something called B sitting there. It doesn't really matter. Okay. The second comment is, and two of you commented on this, and this was really good. It's interesting, you actually wind up proving something that on the surface looks a little bit stronger than what you're required to prove. All you're required to prove is that every left coset is some right coset. In other words, all you're asked to prove, hypothesis, folks, there should be just these huge air raid sirens going off. If you're going to prove something without using the given hypothesis, then something is, I mean, I'll guarantee is 100% wrong, because in all of the problems that we'll do this semester, I've got to be careful, in 99.9% of the problems that we'll do this semester, the hypotheses are required. In other words, if you remove the hypotheses that are given, then the conclusion doesn't necessarily follow. So please get in the habit of looking through your work before you submit it and make sure that you've actually used the hypotheses somewhere. The point is, if you're ever confronted with an expression that looks like this, where G is any element of the group and H is any element of the subgroup, what you get to conclude is that the result lands in the subgroup. What some of you tried to do was write down a stronger version of the hypotheses. What some of you tried to do was say, well, I have something, let's call it H1, that's in H. So, all right, at some point in your proof, you wound up with some element in H, and then you said, so there is a G in the group with, and let's call it H2 in H, with G inverse H2G equals H1. And I saw this on 3 or 4 of your papers, and folks, this hypothesis doesn't, at least not on the surface, imply this one. All this hypothesis says is, if you're confronted with an expression like this, that the result lands in H. It doesn't necessarily say that every element in H is of this form. It simply says that each coset, where you look at the right coset that's generated by the same element that generates as the left coset. And the reason is, if the hypothesis is that AH is HB for some B in the group, that's what we're told, that the left coset AH is some right coset. The question is, why can I conclude that the right coset that I use here is actually the right coset HA? And the answer turns out to be this, but wait a minute. It's always the case that the specific element A is in AH always. If you take a specific element in the group and you look at the coset that it generates, I don't care what subgroup you start with, any subgroup always contains the identity element. So you're always at least looking at AE. In other words, you're always generating the specific element A within its coset. So this is completely independent of this set of hypotheses. This is always true for any subgroup and any element of the group. So in this particular situation, if I've got an element in here, the hypothesis is that it equals this. So here, A is actually in HB, because these two sets are equal. And if it's in this set, then necessarily it's in that set. But now we're going to make a statement about right cosets. As soon as you have an element in the right coset, so HA equals HB, previous work that we did on cosets, the work being, if you have an element that lives inside a coset, then the two cosets have to be equal. Because is that each coset of the form AH is also of the form, well, that's what a left coset looks like, is also of the form a right coset for some. In other words, all you have to do is prove that AH is HB. So there's nothing explicit in the statement that you're trying to prove that says that you're required to prove that this left coset is the same as the right coset generated by the same element you started with. This really is all you're asked to prove. But all of you wind up proving, in fact, not only if you have this condition, is AH equal to a right coset, in fact, you prove that AH is equal to the right coset HA. So question, is this condition, every left coset is a right coset, the same as or somehow weaker than the condition that HA is AH, as all of you proved? And the answer is that they turn out to be the same. So here's an observation. I'm going to call it a proposition because we're going to need it in relatively strong form in about 10 minutes. The proposition is this: if every left coset of H is a right coset of H, then necessarily AH equals HA for all A. So if you give me the information that if you start with a left coset and it happens to be some right coset, I'll tell you which right coset it is. It's that right